There are disasters that announce themselves with thunder. A rocket falls back onto its pad. A booster blooms into a second sun. A capsule falls through the sky beneath a dead parachute, while men on the ground listen to a signal that no longer means rescue. These are public disasters. They break the horizon. They interrupt nations at dinner. They leave wreckage across oceans, deserts, fields, and television screens. Apollo 1 began inside a room small enough to reach across. 3 men lay on their backs inside a spacecraft that was going nowhere. The rocket below them was silent. The engines were cold. The vehicle was not fueled for launch. Cape Kennedy sat beneath the ordinary Florida air of a January evening, humid, flat, and indifferent. On the pad, gantries surrounded the Saturn 1B, like scaffolding around a cathedral whose builders were still arguing over the stone. Inside the command module were Virgil, Gus Grissom, Edward White, and Roger Chaffee. They were not in orbit. They were not beyond the atmosphere. They were not falling toward Earth at 17,000 miles per hour, wrapped in re-entry plasma. They were sitting on the ground during a test. That fact made the day feel safer than it was. The test was called a plugs-out test. The name sounds harmless, almost domestic. It suggests a machine being checked before use, like a lamp on a workbench or a radio on a kitchen counter. In aerospace, plain names often cover elaborate peril. The point of the test was to prove that the spacecraft could run on its own power, separated from external support. For a flight vehicle, this mattered. Apollo had to become self-contained before it could leave the Earth. The capsule had to live alone. So the crew entered the spacecraft. The hatch was sealed. The command module was pressurized. The vehicle began working through procedure. The day immediately became miserable. There was a strange odor in the breathing loop. Communications were poor. Voices broke up. The crew could not hear the ground clearly, and the ground could not hear the crew clearly. The countdown stalled and resumed. The test fell behind. Men with headsets worked problems that should have been boring, yet every delay inside a sealed spacecraft eats at patience. A test pilot can tolerate danger. He has less sympathy for incompetence wearing a headset. Grissom had little patience for the communication system. He was one of the original Mercury 7, a veteran of Mercury and Gemini, a man who had been placed on top of rockets before most Americans had learned to pronounce orbital mechanics. He knew the difference between risk and sloppiness. At one point he asked, with bitter clarity, how they were going to get to the moon if they could not communicate between 2 or 3 buildings. It was a joke only because the alternative was uglier. It was also the kind of sentence investigators should frame and hang above every conference table where managers explain why a problem can wait. Ed White lay beside him in the center couch. White had been the first American to walk in space. During Gemini 4, he had floated above the Earth, tethered to the spacecraft, holding a small maneuvering gun, grinning like a man who had slipped into the outer court of heaven and found the door unlocked. He was athletic, devout, disciplined, and physically steady. NASA liked men like White because he looked like the nation wished to see itself. Calm, clean-cut, brave without theatrical noise. Roger Chaffee was on the right. He was the rookie. No spaceflight yet. 31 years old, quiet, exact, and technically strong. He had the burden all rookies carry in elite groups. He had proved enough to be selected, but not enough to have memory wrapped around his name. Apollo 1 was supposed to change that. He was entering history with 2 men who already belonged to it. The spacecraft around them was the first crewed Apollo command module. The mission was officially AS-204. The name Apollo 1 would come after death, when numbers became memorial language. This was meant to be the first crewed step in the Apollo program, an Earth orbital flight that would test the command and service module before later missions went farther. It was a rehearsal for the road to the moon. Rehearsal is a dangerous word. It tells the mind to relax. It says the real show comes later. Yet in aerospace, a rehearsal can gather many hazards of the real event and strip away the grandeur that reminds everyone to fear them. A rocket on the pad may seem tame compared with a rocket rising on fire. A sealed spacecraft on the ground may seem tame compared with a sealed spacecraft in vacuum. The trouble is that physics does not respect the emotional categories of program managers. At 6:31 p.m. on January 27, 1967, the test stopped being a rehearsal. A voltage transient registered in the spacecraft. Then a voice from inside the cabin reported fire. For a few seconds, the word hung between comprehension and denial. Fire. Inside a spacecraft, the word has no small meaning. A fire in a room offers choices. A man can step back. A door can open. A window can break. Someone can throw a coat over a flame, empty an extinguisher, crawl low beneath smoke, or run outside into the cold night with singed hands and a story to tell. A spacecraft gives no such generosity. A spacecraft is built to isolate its interior from the outside world. It is built to hold pressure, conserve atmosphere, protect its occupants from vacuum, and make escape unnecessary because escape is usually impossible. Apollo 1 was sealed. It was filled with pure oxygen. It was pressurized above the atmosphere outside. The fire moved with savage speed. Materials that might have burned slowly in ordinary air flared under the oxygen-rich conditions. The cabin was packed with wiring, panels, fabric, Velcro, netting, hoses, and equipment. The volume was small. The crew were strapped down. The hatch opened inward, and as the fire heated the cabin gases, pressure rose. The rising pressure held the hatch shut with the cruelty of perfect mechanics. White, in the center couch, had the job of opening it. He tried. The spacecraft refused. Outside, technicians and pad workers heard the calls and fought toward the command module. Smoke filled the white room around the capsule. Heat and toxic gases forced men back. They returned. They tried again. The access was poor, the procedure slow, the hardware stubborn. The rescue effort became a contest between men and a machine designed around the wrong emergency. The machine won. By the time the hatch was opened, Grissom, White, and Chaffee were dead. The first crewed Apollo spacecraft had killed its crew before leaving Earth. No lunar crater did it. No meteorite did it. No deep space radiation, no re-entry plasma, no guidance failure at the edge of the unknown. Apollo 1 burned on the launch pad, inside reach of ladders, cables, men, voices, and the entire industrial might of the United States. 3 astronauts died in a spacecraft that was connected to the ground by equipment, procedure, and hope, yet remained unreachable in the seconds that mattered. The moon program had met its first fatal truth. A nation can build a machine meant to cross the heavens and still fail to make it safe enough for 3 men to sit inside on Earth. To understand Apollo 1, begin with the machine. The Apollo Command Module was one of the most ambitious crewed spacecraft ever built at that time. Mercury had been a capsule for 1 man. Gemini had carried 2 and taught America the techniques it needed for the moon. Rendezvous, docking practice, long-duration flight, spacewalking, precision control. Apollo was a different order of machine. It had to carry 3 men through Earth orbit, toward the moon, around it, and back. It had to survive launch, separation, deep space flight, re-entry, and recovery. It had to function as cockpit, pressure vessel, life support chamber, navigation station, sleeping space, and lifeboat. It had to be light enough to fly. That requirement is the tax collector of spaceflight. Every bracket, wire, latch, valve, panel, and handle must justify its mass. A pound added here becomes a penalty there. The rocket must lift it. The structure must bear it. The mission must carry it. Weight is never local in a spacecraft. It travels through the whole design like guilt through a family. The command module was shaped like a blunt cone, a form dictated by re-entry. Its broad heat shield would face forward into the atmosphere as the spacecraft returned at enormous speed. The crew sat inside above that heat shield, surrounded by displays and controls. Beneath panels and behind compartments lived the working body of the spacecraft. Electrical wiring, environmental control hardware, instrumentation, plumbing, structural members, communications gear, and access points that technicians had to reach during assembly and test. Diagrams make spacecraft look orderly. Real spacecraft, especially test spacecraft, are more like arguments packed into aluminum. Every system wants space. Every system wants access. Every system wants margin. The wiring must go somewhere. The hoses must go somewhere. The crew must reach switches. Technicians must inspect equipment. Emergency procedures must fit through human hands under stress. A spacecraft interior is a compromise made physical. The Apollo 1 command module was a Block 1 spacecraft built by North American Aviation. Block 1 was designed for Earth orbital missions, not lunar landing. The later Block 2 command module would include changes needed for lunar operations, including docking with the lunar module. Even so, Block 1 was vastly more complex than Mercury or Gemini. More capability meant more interfaces. More interfaces meant more failure paths. A disaster rarely needs every part to fail. It needs enough parts to cooperate. On January 27th, the cooperation was lethal. The most famous element was the atmosphere. NASA had chosen a pure oxygen atmosphere for its early spacecraft. There were engineering reasons. A pure oxygen system at low pressure simplified life support and reduced structural mass. The crew needed oxygen. Nitrogen added complexity and raised concerns about decompression sickness if pressures changed too quickly. Mercury and Gemini had used pure oxygen, and those programs had succeeded. Success has a way of bleaching danger until it looks like tradition. In flight, a low-pressure, pure oxygen atmosphere made sense within the assumptions of the period. On the ground, Apollo 1 was different. During the plugs-out test, the cabin was filled with pure oxygen at pressure above the surrounding atmosphere. This allowed leak checks and simulated aspects of flight operations, but it created a severe fire hazard. At higher pressure, with oxygen as the whole breathing environment, materials become more willing to burn. Sparks become more dangerous. Fabrics, plastics, and insulation can burn faster and hotter than intuition expects. The spacecraft was sitting on Earth, yet its atmosphere had made it less forgiving than many rooms in orbit. Fire requires ignition, fuel, and oxygen. Apollo 1 had the oxygen in abundance. The fuel was distributed throughout the cabin. Velcro became a symbol after the accident, partly because it was everywhere, and partly because the symbol was easy to understand. Astronauts liked Velcro. Engineers liked Velcro. It solved small problems in a spacecraft where loose objects can float, drift, jam, vanish, or strike a crewman in the eye. Velcro made things stay put. Checklists, tools, bags, and small equipment could be fastened where the crew needed them. It was light. It was flexible. It was convenient. Convenience is a poor fire code. The cabin also contained nylon netting and other combustible materials used for stowage and restraint. Some of these materials had been accepted because the fire risk was viewed through assumptions that no longer applied once the capsule was pressurized with pure oxygen on the pad. A material choice that seems tolerable in one environment can become grotesque in another. The same strip that keeps a checklist from floating away can become part of the flame path. The ignition source was never determined with final certainty. That uncertainty matters. Investigators traced the most likely origin to an electrical fault, probably in the lower left area of the cabin, near environmental control equipment and wiring. There had been workmanship issues. There had been damaged wiring concerns. There were bundles routed through crowded spaces, places where insulation could be abraded, and opportunities for an arc to become the first sentence in a fatal story. Electrical failures have a particular menace because they can begin quietly. A wire chafes. Insulation weakens. A conductor touches where it should not. A spark appears in a place no flame belongs. In a normal environment, the result may be smoke, a blown circuit, a scorched panel, a maintenance action, and a technician muttering at a form. In Apollo 1, the spark entered a cabin ready to answer. The hatch completed the trap. The Apollo 1 hatch assembly was slow to open under normal conditions. It included an inward opening inner hatch and other outer elements, with a procedure that took time and coordination. The design had been shaped by concerns about pressure integrity and the lessons of earlier spaceflight. In 1961, Grissom's Mercury capsule, Liberty Bell 7, sank after splashdown when its hatch blew prematurely. That event influenced thinking about hatch safety. Designers had reasons to fear a hatch opening when it should stay closed. Apollo 1 revealed the opposite danger. A hatch can be too loyal. When the cabin fire began, pressure rose rapidly. The inward opening hatch could not be pulled open against that pressure. The crew needed a fast path out. The spacecraft offered a puzzle box. Under normal conditions, the hatch could be opened with procedure. During the fire, procedure became a slow prayer in a room with no oxygen left to spare. A hatch reveals what its designers feared. Apollo's hatch feared the outside. It did not fear the inside enough. The command module was built to survive vacuum, launch stress, and flight. It was not built to release a crew quickly from a high-pressure oxygen fire during a pad test. That failure was not a single oversight. It was a pattern of thought. The spacecraft had been treated as a flight article, and the ground test as a step toward flight. The ground condition itself had not been feared with enough precision. That is one of Apollo 1's most severe lessons. Danger does not wait for the mission phase. That sounds dramatic. A ground test can kill. A pad can become a tomb. A capsule can behave like a spacecraft and a furnace at the same time. The men inside Apollo 1 were not passive passengers in this system. They were test pilots, engineers by habit, if not always by title, and relentless critics of bad machinery. Grissom especially had a reputation for bluntness. He was not theatrical. He was the sort of man who looked at a machine and expected it to earn trust with behavior, not promises. He had reason to worry. The Apollo spacecraft had been troubled. North American aviation faced pressure over quality, schedule, and workmanship. NASA had found deficiencies. The spacecraft had too many open items. The astronauts themselves complained about the condition of the vehicle. A famous story has Grissom hanging a lemon on the spacecraft or simulator as a dark joke about its defects. The details have been repeated in several forms, as happens with symbols, but the meaning survives without much help. The crew did not think the spacecraft was ready, yet the test went forward. This is where the story leaves the hardware and enters the system around it. Apollo was never merely an engineering program. It was a national vow. In 1961, President Kennedy had committed the United States to landing a man on the moon and returning him safely to Earth before the decade was out. The sentence was grand, clear, and almost reckless in its ambition. It gave NASA a destination, Congress a price tag, industry a feast, and the Soviet Union a signal. America was no longer going to answer each Soviet first with embarrassment and improvisation. It would choose a goal so large that the entire contest would be redefined. the Soviet Union had drawn first blood in space prestige. Sputnik entered orbit in 1957 and changed the sound of the Cold War. A small beeping satellite made American power look suddenly earthbound. Then came Yuri Gagarin in 1961, the first human in orbit. More Soviet achievements followed. The American public watched a rival system claim the heavens, one headline at a time. Apollo was the answer. It had majesty. It also had a deadline. The end of the decade became sacred. That date lived inside design reviews, budgets, contractor schedules, public speeches, congressional hearings, and private fears. NASA moved at astonishing speed because it had to. The agency had greatness in its bloodstream. It also had haste in its bones. Haste does not always look like panic. Often it looks like paperwork completed on time. A great technical program can normalize pressure so deeply that people stop hearing it. No manager has to pound the table every morning. The schedule is present before anyone speaks. Contractors know it. Engineers know it. Astronauts know it. Review boards know it. A national goal becomes a silent participant in every meeting. Mercury and Gemini had given NASA confidence. That confidence was earned. The agency had placed Americans in space, learned orbital maneuvering, proven long-duration missions, and conducted spacewalks. It had built a technical culture able to solve problems faster than many older agencies could describe them. The United States had begun to close the gap with the Soviets. Earned confidence can become dangerous when it starts spending credit from the future. Apollo was larger than anything NASA had flown with men aboard. Its complexity outpaced the habits formed by Mercury and Gemini. Yet the organizational rhythm of success continued. Problems were expected. Problems were worked. Problems were accepted until fixed. The machine would be improved. The next review would catch more. The next test would teach. The next version would be cleaner. This is how danger becomes polite. It is given an action item. The men who built Apollo were not fools. Many were brilliant. Many worked brutal hours under immense pressure. Many understood the risks. The tragedy is harsher because it did not arise from cartoon incompetence. It arose from a system filled with capable people whose combined decisions still produced a lethal condition. A bad system can make good men sign bad forms. North American Aviation, the prime contractor for the command module, had won one of the most difficult assignments in aerospace history. Its engineers had to design and build a spacecraft for a mission whose details were still evolving. NASA made changes. The lunar mission architecture changed as the program matured. Weight limits tightened. Requirements multiplied. The contractor struggled. NASA pushed. Everyone was trying to build the future while living inside a stopwatch. The Block 1 spacecraft showed the strain. The crew complained of poor workmanship. Inspectors found problems. The command module was cluttered, difficult to work in, and far from the disciplined machine it needed to become. In a slower program, those conditions might have halted everything earlier. In Apollo, they became part of the mountain everyone was already climbing. There is a type of managerial optimism that sounds noble until it is read after an accident. It says the remaining problems are manageable. It says the team is working them. It says the test will provide data. It says risk is inherent in the enterprise. All of those statements can be true. A coffin can be built from true statements. Before the fire, NASA and its contractors knew about oxygen fire hazards. They knew about combustible materials. They knew about hatch limitations. They knew about wiring concerns. They knew about workmanship flaws. Each fact existed somewhere in the system. The fatal failure was that these facts were not combined into an unbearable picture soon enough. Apollo 1 was caused by tolerated knowledge. That phrase is colder than ignorance. Ignorance can claim innocence. Tolerated knowledge cannot. It means people knew enough to worry, but not enough, or not loudly enough, or not in the right room to stop the test. The hazard lived in fragments. The fire assembled them. The plugs-out test proceeded because, within the working assumptions of the program, it was acceptable. The crew suited up. They entered the spacecraft. The hatch was sealed. The cabin atmosphere was changed to pure oxygen. The pressure rose. The test moved through its steps. Problems appeared, but none of them carried the emotional force needed to break the day apart before the fire did. That detail matters. Disaster often begins as nuisance. The smell in the breathing loop, the poor communications, the held countdown, the crew irritation, the gradual fatigue. None of these were the fire, but they shaped the setting in which people judged the test. By evening, the operation had already become frustrating and delayed. The human mind is a poor instrument under accumulated annoyance. It begins to sort problems into another one rather than the one. Inside the capsule, the men waited. Grissom on the left, White in the center, Chaffee on the right. They wore pressure suits. They were connected to life support. Their couches placed them on their backs, angled upward, facing panels and windows. Around them was the snug complexity of Apollo. Switches, displays, checklists, straps, controls, and the dense equipment of a spacecraft still proving itself. Outside, ground teams monitored the test. The white room surrounded the hatch area. The gantry enclosed the vehicle. Technicians had access, but not instant access. A spacecraft on a launch pad is close and far at the same time. It is yards away from human hands, yet separated by platforms, covers, seals, procedures, and the fact that flight hardware cannot be treated like a jammed garage door. The countdown was held at T-minus 10 minutes. The test had not reached completion. Then, at 6:31 p.m., the electrical anomaly appeared. The first report of fire came from the crew almost at once. The ignition source likely began low in the cabin, near the left side, though the exact origin was never established. A spark or arc in damaged wiring remains the strongest explanation. The fire spread upward and outward. In the pure oxygen atmosphere, flame moved along materials with terrifying speed. The cabin, already pressurized, heated rapidly. The crew's first problem was recognition. The second was escape. There was no time for a long diagnosis. In the transcripts and later reconstructions, the voices come through as fragments of men inside a sudden emergency. They report fire. They identify it as serious. They move toward egress. White begins the hatch procedure. The hatch does not open. The pressure rises. The cabin becomes a pressure vessel in revolt. The crew cannot simply push the hatch outward because it does not open that way. They cannot pull it inward because the pressure is now against them. The procedure that might have worked under calm conditions becomes useless under the conditions that matter. Pressure, heat, smoke, toxic gases, flame, and time converge on three men strapped into couches. Here the story becomes almost unbearable because the physical chain is so clear. An electrical fault likely ignites material. Pure oxygen accelerates combustion. Combustible cabin contents spread flame. Heat raises internal pressure. Pressure prevents hatch opening. Poor access slows rescue. Smoke and toxic gases overpower the crew. No single link needs malice. The chain only needs contact. Outside, pad workers try to reach them. The fire produces thick smoke. The white room fills with toxic gases. Visibility collapses. Men struggle to breathe. They move forward, retreat, come back, and work at the hatch. The rescue attempt becomes heroic in the plainest sense. Men doing dangerous work because men inside are dying. Yet heroism meets hardware. Hardware is unmoved by motives. The first attempt to reach the crew is slowed by the pad configuration and by the difficulty of the hatch. Workers do not have a simple lever to pull that frees the astronauts. They must fight through layers of access and procedure, while the cabin has already become unsurvivable. The spacecraft wall ruptures under pressure. That rupture changes the fire. But by then, the crew has already been exposed to lethal smoke and gases. Within a short time, all three are dead. Later medical findings show asphyxia from toxic gases as the primary cause, with burns also present. The phrasing is clinical because reports must be clinical. The reality is that the crew were poisoned and burned while trapped inside the machine they were meant to command. The hatch is finally opened minutes after the fire begins. Inside, the command module is blackened. The interior is charred and toxic. The astronauts are still in their couches, though their positions show the struggle to escape. White had tried to reach the hatch. Grissom and Chaffee were caught in the same nightmare of straps, smoke, flame, and failed design. Recovery is difficult. It takes hours to remove the bodies. That is a detail often passed over because the mind wants the story to move to investigation, hearings, and redesign. Yet there is a brutal dignity in staying there a moment. The aftermath of a spacecraft fire is not clean. The men who entered that capsule after the fire carried out work no one should have to do. Their task was technical, procedural, and intimate. They were retrieving colleagues from a machine that had betrayed them. NASA had lost astronauts before, but not in a spacecraft. Several members of the astronaut corps had died in aircraft accidents. Test pilots lived near death. The culture understood risk in jets, training flights, and high-performance aircraft. Yet Apollo 1 was different. The men died inside the national vehicle, inside the program meant to reach the moon. The spacecraft itself became the site of death. That changed the meaning. The families were notified. Betty Grissom, Pat White, and Martha Chaffee joined the private roll of those who pay the human invoice for public greatness. Astronaut wives in the 1960s lived under a strange bargain. They were expected to smile for photographs, support the mission, absorb fear quietly, and perform composure as a civic duty. America wanted heroes, and heroes require families who can be photographed without showing the full cost in their faces. The cost arrived anyway. Grissom left behind a wife and children. White left behind a wife and children. Chaffee left behind a wife and children. 3 households were broken by a ground test whose very name sounded routine. That point should never be softened. The astronauts were public men, but they were not public property. NASA now had to explain. The agency could not hide the accident. The American space program was public in a way the Soviet program was not. The astronauts were famous. The press was present. Congress had power. Contractors had names. Families had voices. The fire took place at Cape Kennedy, inside a national program whose existence depended on public funding and political trust. The deaths were announced. The nation mourned. Then the investigation began. The Apollo 204 Review Board was formed to determine what had happened. Its task was technical, but the meaning was larger. NASA had to examine the spacecraft, the test, the contractor, the safety culture, and the assumptions that had placed the crew in that cabin. The board had to ask questions that could damage reputations, schedules, and contracts. It also had to produce findings strong enough to prevent another fire. This was not a Soviet-style erasure. No one pretended the men had never existed. No one scrubbed Grissom, White, and Chaffee from photographs. The disaster became public knowledge. Congressional hearings followed. The program paused. The spacecraft was redesigned. Yet any account that paints the aftermath as pure transparency misses the human and agency instinct for self-protection. NASA had to tell the truth while preserving Apollo. That is a difficult and morally hazardous posture. Say too little, and the dead become insulation for management. Say too much in the wrong way, and the lunar program might collapse under political fury. The agency held a mirror and a shield at the same time. The posture was awkward because it had to be. The findings were severe. The review board concluded that the fire most likely started from an electrical source. It emphasized the pure oxygen atmosphere, the rapid spread of flame through combustible materials, the vulnerability of wiring and plumbing, the hatch design, and emergency access failures. It identified serious weaknesses in design, workmanship, and test readiness. None of those findings required poetry. They were damning in plain language. The spacecraft had not been safe enough for the test that NASA chose to conduct. That sentence sits at the center of Apollo 1. The most important thing about the fire is that it was not mysterious in the way people often mean mysterious. The exact spark remained uncertain, but the system-level failure became painfully clear. Once the fire began, the spacecraft gave the crew almost no chance. The atmosphere fed it. The materials carried it. The pressure trapped them. The hatch slowed escape. The pad setup slowed rescue. The emergency had been designed into the margins. The command module was treated as a spacecraft. It also needed to be treated as a room where 3 men might need to get out in seconds. That distinction killed them. After the fire, Apollo changed. The hatch was redesigned to open outward and open quickly. This was one of the most visible changes because it answered the most haunting image of the accident. White struggling against a hatch that pressure would not release. The new hatch could be opened far faster, giving future crews a real chance during pad emergencies. The cabin atmosphere for ground testing changed. NASA abandoned the practice of placing crews inside a high-pressure, pure oxygen cabin during such tests. Mixed gas would be used on the pad, with pure oxygen at lower pressure used later in flight conditions. This change directly addressed the fire environment that made Apollo 1 so deadly. Combustible materials were removed or replaced. Velcro and nylon were scrutinized. Materials had to meet tougher flammability standards. The interior of the spacecraft became less friendly to flame. Wiring was rerouted, protected, and inspected with greater rigor. Plumbing was improved. Quality control was tightened. The relationship between contractor and agency received new attention. North American aviation came under harsh criticism. So did NASA management. There were congressional hearings, and those hearings revealed the uncomfortable truth that the lunar program had been moving with a tolerance for risk that now looked far too casual. Joseph Shea, a key Apollo manager, became one of the figures associated with the program's pre-fire management failures, though the story is larger than any one man. Shea had been brilliant, intense, and deeply involved in driving Apollo forward. After the fire, he became one of the people marked by the catastrophe. The system needed accountability. It also needed to keep enough talent to repair itself. That is one of the cruel balances after disaster. The people who fail to prevent it may also be among those who best understand how to fix the machine. Purging everyone can satisfy anger and cripple memory. Protecting everyone can turn reform into theater. NASA had to move between those dangers while the moon deadline still loomed. The Apollo program paused for 20 months before another crew flew. That pause was costly. It also saved lives. Apollo 7 launched in October 1968 with Wally Schirra, Don Isley, and Walter Cunningham aboard. It was the first crewed Apollo mission after the fire. The spacecraft performed successfully in Earth orbit. The mission was not glamorous in the way Apollo 8 or Apollo 11 would be, but its success mattered deeply. It proved that Apollo could fly men again after killing its first crew. Then came Apollo 8. In December 1968, Frank Borman, Jim Lovell, and Bill Anders circled the moon. They became the first humans to leave Earth orbit and look back at the whole Earth from lunar distance. The images and broadcast entered the civic memory of the 20th century. The world saw Earth rising over the moon, blue and white above gray desolation. It was one of the rare moments when technology produced wonder without needing a salesman. Then came Apollo 11, July 1969. Armstrong and Aldrin on the surface, Collins alone in lunar orbit. The landing at the Sea of Tranquility, the flag, the boot prints, the line everyone remembers. A triumph so bright it has a habit of bleaching the scorched concrete beneath it. Apollo 1 belongs beneath that triumph. Beneath, not behind. It was not a mere prelude. A prelude exists to serve the music that follows. Grissom, White, and Chaffee were not narrative fuel for Apollo 11. They were men killed by preventable conditions in a spacecraft that had not yet earned the trust placed in it. The later success of Apollo does not redeem the fire. It only proves that the program learned enough from the dead to stop repeating the same form of error. That is a stern kind of honor. A better spacecraft flew because 3 men died in a worse one. The sentence feels ugly because it should. The engineering autopsy of Apollo 1 begins with a simple principle. A spacecraft is an environment, not a shell. That means no subsystem can be judged alone. Atmosphere, materials, wiring, pressure, hatch design, crew procedure, emergency access, pad support, and management assumptions all interact. A decision made for weight can affect fire risk. A decision made for pressure integrity can affect escape. A decision made for convenience can affect flame spread. A decision made for schedule can affect inspection. A decision made in one office may kill a man in another compartment. Apollo 1 shows the failure of separated thinking. The oxygen atmosphere was treated as a life support choice. The combustible materials were treated as stowage and interior design choices. The hatch was treated as a pressure and safety choice. The wiring was treated as an electrical and workmanship matter. The test was treated as a procedural step. The fire treated them as one system. That is the genius of disaster. It understands the machine better than the organization does. In the purest technical sense, Apollo 1 taught NASA to fear fire in crewed spacecraft with renewed seriousness. That lesson reshaped material standards, atmospheric procedures, emergency egress, and configuration control. These were not decorative reforms. They changed hardware. They changed tests. They changed inspection habits. They changed how future crews would sit inside Apollo spacecraft before launch. Yet the deeper lesson concerns normalization. Before the fire, warnings existed. Many were specific, some were cultural, some came as complaints, some as discrepancy reports, some as jokes, some as unease among men who had been inside enough machines to sense when one had bad character. NASA had a system for processing such concerns, but the system did not force the decisive conclusion in time. After the fire, the same facts looked obvious. This is common after disasters. The mind looks backward and says the signs were clear. That can be true, but it can also be a comforting lie. In real time, signs are mixed with noise, pressure, habit, loyalty, ambition, fatigue, and the desire to keep moving. A problem that glows red after an accident may have looked amber before it. Programs run on amber. They have to. No complex machine reaches readiness with every concern extinguished. The difference between acceptable amber and lethal amber is the art that keeps people alive. Apollo 1 failed that art. It accepted too much. The United States asked NASA for greatness on a timetable. NASA asked contractors for miracles under contract. Contractors asked engineers and technicians to make unfinished designs real. Astronauts accepted risk because that was the profession and the calling. Each level transmitted pressure downward and confidence upward. Somewhere in that flow, danger stopped sounding like danger. The fire restored the proper vocabulary. It did so brutally. There is a temptation to turn Apollo 1 into a story of lost innocence. That is not quite right. NASA was never innocent. It was an agency born in missile technology, Cold War rivalry, test pilot culture, and national competition. Everyone involved knew spaceflight was dangerous. The issue was more specific. Apollo 1 destroyed the illusion that bravery could compensate for poor ground assumptions. A test pilot can accept the risk of flight. He should not be asked to accept a trap masquerading as procedure. Grissom, White, and Chaffee did not die because space demanded their lives. They died because a spacecraft on the ground contained a fire environment and an escape design that made survival impossible once ignition occurred. The distinction matters because it preserves responsibility. The moon is silent. Physics is indifferent. Men and agencies make choices. The Apollo 1 crew had different relationships to the future they were building. Grissom had already paid dues in the early American space program. His first mission, Liberty Bell 7, ended with controversy when the hatch blew after splashdown and the capsule sank. For years, Grissom lived with unfair suspicion from some corners, though later evidence and analysis supported his account that he had not intentionally blown the hatch. Gemini 3 gave him another flight and another chance to prove what those who knew him already understood. He was skilled, tough, and reliable. He was also wary. By Apollo 1, Grissom had been around enough spacecraft to know the difference between development trouble and danger. His complaints carried weight because he was no rookie alarmist. When men like Grissom distrust a spacecraft, the spacecraft should have the decency to blush. White represented another side of NASA's self-image. His Gemini 4 spacewalk had been an emotional milestone. America had watched one of its own move outside the spacecraft, free in orbit, tethered to the machine and to the Earth below. White's reluctance to end that spacewalk became part of his legend. He had to be told to come back in. There was wonder in that moment, majesty too. A man floating outside the world, unwilling to return to the cramped capsule because the open sky of orbit had briefly become home. Apollo 1 killed him in the opposite condition. No openness, no Earth below, no freedom of motion, only a sealed cabin and a hatch he could not open. Chaffee carried the tragedy of the unflown. He had trained, qualified, and entered the astronaut corps at a moment when Apollo was about to define the era. He was assigned to a crew with 2 proven men. His future was ahead of him in the clean, cruel way of men selected for dangerous greatness. He never reached orbit. His spaceflight career exists as preparation, photographs, technical work, family memory, and the right-hand couch of a burned command module. The public often remembers the firsts. First American in space. First American spacewalk. First man on the moon. First words from the surface. Chaffee reminds us that history also contains men who trained for firsts and instead became warnings. The warning was heard. That matters. Apollo after the fire was not the same program. The redesigns were real. The shift in materials and atmosphere practice was real. The hatch change was real. The scrutiny grew sharper. NASA's later success depended in part on a humbled understanding of how a system could kill. Yet humility has a shelf life, unless it is maintained. The space program would face later disasters. Challenger in 1986, Columbia in 2003. Each would expose new patterns of normalized risk, managerial pressure, technical warning signs, and official confidence stretched beyond evidence. Apollo 1 did not inoculate NASA forever. No disaster does. Lessons are not inherited automatically. They must be carried, taught, refreshed, and made unpleasant enough to survive the next schedule meeting. A safety lesson that becomes ceremonial is already dying. Apollo 1's lesson remained embedded in hardware for the lunar program, but the broader human pattern would return. The machine changes, the pressure changes clothes. The old temptation finds a new acronym. That is why Apollo 1 remains more than an early tragedy. It is a case study in how great systems fail while staffed by capable people. No serious account needs a villain twisting a mustache beside the gantry. The culprit is more familiar and more frightening. Schedule pressure, fragmented responsibility, accepted defects, overconfidence from past success, design choices that made sense in isolation, and a national mission that made delay feel like betrayal. The machine did exactly what physics allowed. The system had allowed the machine. There is dark majesty in Apollo because it did reach the moon. A free people built machines that crossed 250,000 miles of void and returned men to Earth. That achievement still amazes because it deserves to amaze. The lunar program remains one of the few modern feats that can bear the word greatness without sounding dressed for a parade. But the greatness has a shadow. Launch Complex 34 became part of that shadow. After Apollo 1, the pad continued to exist as concrete, steel, weathered structure, and memory. The Saturn 1B would launch from there again, but the site would never lose the meaning of January 27th. Over time, the old complex became quiet. The service structures were removed. The launch pedestal remained. Visitors who stand there do not see the full machine. They see absence given shape. There is a plaque at the site. It honors Grissom, White, and Chaffee. The words ask visitors to remember them and the sacrifice they made in the cause of exploration. Memorial language has a hard task. It must be dignified without becoming too smooth. It must honor sacrifice without making death seem like a bill that history was always entitled to collect. Apollo 1 deserves remembrance, but remembrance should keep its edges. The men did not vanish into noble abstraction. They died in a specific machine, under specific conditions, after specific warnings, because specific choices failed. That specificity is the tribute. General grief is easy. Accurate grief is harder. Stand at Launch Complex 34 in the mind for a moment. Not during the fire. After. The rocket is gone. The gantry no longer crowds the sky. The Florida air moves through concrete openings where men once worked under impossible deadlines. The pad that once held a national ambition now holds silence, weather, and names. The moon is still there, bright and indifferent. It has no opinion about the men who died trying to reach it. The memorial does the human work the moon cannot do. It remembers. The road to Tranquility Base did not begin with a footprint. It passed first through a sealed hatch on Earth. Inside that hatch, 3 men lay on their backs during a test that should have ended in paperwork. They were surrounded by oxygen, wiring, flammable material, pressure, and the confidence of a country in a hurry. When the fire came, the spacecraft became honest. It revealed every bad assumption at once. The nation would still reach the moon. Apollo would still become legend. Armstrong would still descend the ladder. Aldrin would still stand beside him. Collins would still orbit alone above the far side, carrying solitude in a machine made safer by grief. The photographs would still inspire wonder. Children would still look up at the moon and feel the old human ache to go there. But before all that, there was Pad 34. There was Grissom, who did not trust the spacecraft enough. There was White, who tried to open the hatch. There was Chaffee, who never got his first flight. There was a command module blackened from within. And there was a lesson written in fire, plain enough for any engineer, manager, pilot, or nation willing to read it. The heavens punish arrogance from a distance. Machines punish it up close.